Hi, I'm Paul. We're doing Leetcode must-know interview questions. Today's challenge is single number 2. The last one we did was single number. That was rated as easy. And this one is rated as medium, although this seems like a hard problem to me. Even to explain it is hard. Or to explain the approach is hard. But anyway, the challenge is given an integer array nums where every element appears 3 times except for 1, which appears exactly once. Find the single element and return it. You must implement a solution with a linear runtime complexity and use only constant extra space. Okay, well, that's what makes it difficult, because obviously you could just iterate through the array and keep track of how many times you see each number and return the one that only appears once. Is that going to use constant extra space? No. So we have to, and again, we're still in the bit manipulation category here, so I'm going to pause this for a minute and write some stuff up that may get us started, and then we'll go from there. Okay, so what we want to do, I mean, if you think about this, all the numbers in the array, if we added them all up in binary format, well, let's do it another way. Well, let's say we have all the numbers in binary and we add the number of bits, set bits. We add the number of 1 bit for each position. That's going to be 32 bits. And because every number except 1 appears 3 times, then the sums are all going to be multiples of 3, except where the single number has contributed a bit. So we can use that fact to extract the single number. Now, you know, we can't really write a program to do it that way, but we can use the same principle to keep track of the number of bits. We're going to use two variables, like 2 buckets, called 1 and 2, and what I've got here is well, it's if you've seen truth tables before, that's what we have on the left-hand side of the line. On the right-hand side, okay, so let's see what's going on here. Here's our counters, 2 and 1. I mean, every bit, now there's 32 bits, but every bit obeys the same rules. So we only really have to consider 1 bit. Here's our counters, 2 and 1. If we get a 0 bit, that doesn't change anything. So the values in 2 and 1 after we see a 0 bit are exactly the same. Now, what if we see a 1 bit? Well, if we see a 1 bit and the counters are, actually I should explain what's happening here on line 4. This can't happen. I mean, we can't have a bit that's been seen exactly once and exactly twice. So those, and the same thing on the last line here. For this one, if a 1 comes in and the 2 and 1 counts are both 0, then we add 1 to the 1 counter, right? If a 1 comes in and the 1 counter is 1 and 2 counter is 0, then we remove the 1 from the 1 counter and add it to the 2 counter. If another 1 comes in and the 2 counter is 1 and the 1 counter is 0, then we just throw it out, because that means we've seen the number 3 times. and that's not what we want. All right. We can convert this into Boolean algebra expressions, and I'll leave the whole exercise of how to do that to the viewer, but kind of an intuitive explanation of this is the one variable. All right, if a number comes in and we have already seen it one time, we're using this principle of exclusive ORing a number with itself that we used in the previous in the previous challenge. If you exclusive OR a number with itself, it becomes 0. So if we've seen the number before, we want to remove it from, if we've seen it once, we want to remove it from the one column, but only if it is not in the 2 column, only if we have not seen it twice. Okay. The 2's. All right, same thing. If we've already seen it twice, we want to remove it, but only if it is not in the 1 column. It can only be in the 1 column. We can't put it in the 1 column if we've already seen it twice. That's what this is up here. If we've already seen it twice, we can't put it in the 1 column. So if it's in the 1 column, then we can't remove it from the 2 column. If you want to see how this works, in relationship to the table, let's take a look at it like this. So we have the exclusive ORs of 1 and 1 and the number from the array. Where do we have exclusive ORs? All right, so one of them is here. This is an exclusive OR and not 2, so 1 is still 1. All right, this line we don't care about. Exclusive OR. Okay, here we have an exclusive OR with 1 and the array number, not 2, and so the 1 variable becomes 1. Down here we have an exclusive OR, 0 and 1, but not 2 is not true. Therefore, 1 stays at 0. Here's how it works with the 2. Let's find exclusive ORs with the 2. Okay, here's 1. Exclusive OR with the 2, not 1 is true, so that stays at 2. Okay, down here, exclusive OR with the 2, 1 and 0. But we compute the 1 first. So really we have to look over here. So we've already put this as 1 in the 1 variable. So not 1 is false, and the 2 variable doesn't change. Let's look at this one. This is an exclusive OR. The exclusive OR is true. Again, we've got to look over here. Now we have not 1 is true. So the 2 changes to a 1. Okay. I'm going to try to do one more thing here, and that is to work through example 1, where the input numbers are 2, 2, 3, and 2. You can see those here in binary 2, 2, 3, 2. And then work through the computations, the Boolean algebra computations, and see what happens. So we have, in the first one, we have 1, and we're going to exclusive OR it with AI. The first one, which is this one, 1 to 0, exclusive OR with 1, 0, and we get 1, 0. and then we AND it with not 2. Not 2 is, since 2 is 0, 0, not 2 is 1, 1. AND it with 1, 0, and we still have 1, 0. Okay, now we do the computation on 2. So we have 2, exclusive OR with AI. Exclusive OR, and that is 1 and 0. And then we AND it with not 1. 1 is 1, 0, so not 1 is 0, 1. Now if we AND 1, 0 and 0, 1, we're going to get 0, 0. Okay, so we're done with that one. Done with that. Go to the next number, 1, 0. Do the computation again. Exclusive OR. 1 and AI. Now we have seen that number before, so when we exclusive OR it, it actually gets removed here. And now we have 0, 0. We AND that with not 2. 2 is 0, 0. So not 2 is 1, 1. And if we AND 0, 0 and 1, 1, we get 0, 0. Okay, do the computation on 2. 2, exclusive OR with AI. That is going to be 1, 0. Okay. Let's see. And then AND it with not 1. 1 is 0, 0. Not 1 is 1, 1. If we AND this, it doesn't change. It's 1, 0. So you can see what's happened here so far is that we had the number 2 where we saw it once. Now we have seen the number 2 twice. Let's go to the next number. The next number is 3. All right, exclusive OR 1, which is 0, 0, with 3, which is 1, 1. All right, so that exclusive OR actually gives us 1, 1. That means we have seen the number 3 once. We AND it with not 2. Not 2 is 0, 1. So actually if we AND 0, 1 with 1, 1, we get 0, 1. Okay. Now we'll do the computation on 2. So 2 exclusive ORed with AI, which is 1, 1. Exclusive OR, we get 0, 1. And we AND it with not 1. Not 1 is 1, 0. So if we AND that, we actually get 0, 0. Right? So that is done. And finally, 1 exclusive OR with AI, which is 2. All right, if we exclusive OR 0, 1 and 1, 0, we get 1, 1. AND it with not 2. 2 is 0, 0, not 2 is 1, 1, so we AND it. We still have 1, 1. All right, 2. It really doesn't matter at this point what we do with the 2. But let's work it through. 2 exclusive OR with AI is 1, 0. AND it with 1, 1. Well, 1, 1 is 1, 1. AND it with 1. 1, 1 is 1, 1. Not 1 is 0, 0. So what we have here is 0, 0. And the final result of this is the number that we have seen one time. And that's it right there, 3. Everything else has canceled out. So it's a long explanation. It's much longer than the implementation. So let's go ahead with that. All right, so we need two variables here. We call them 1 and 2. All right. We're going to go through every number in the array. So for int num in, do I need the index here? I don't think so. For int num in nums, 1 equals 1 exclusive OR with num, and then end it with not 2. And 2 equals 2 exclusive OR with num, and it with not 1. I don't need that. Okay, now again, what we want to happen here is, first time we see a number, 1 will have it. The second time we see a number, 1 will remove it and 2 will add it. The third time we see the number, 1 will not be able to add it because it's already in 2. 2 will remove it. And so at the end, we just have one number left in 1. If you're not totally comfortable with all this Boolean algebra, neither am I, which is why I'm a little nervous about this. But let's try it. Wrong answer. Oh my God. Okay, hang on. All right, so I can see there's a typo here. I hope that's the only issue. All right, let's try it again. All right, so that one did work for the base cases. Let's pull it over here and submit the thing. Okay, it's good. A good time too. I think some people cheated on this. There's no reason for, what is this over here? This is 6 milliseconds. This is like, this is, rounding. There's no reason for a solution to take 6 times as long if people are following the rules, which is, constant space, linear runtime, and I mean, let's take a look here. I don't know how many times I can analyze the I know what the complexity is. Let me analyze the memory first. It should say like O of 1, right? Yeah, so the space complexity is O of 1. So that is constant. And usually if you're not like a paying member, it only lets you analyze complexity once a day. I don't know if that's applies to like one memory and one runtime or one total. Oh, yeah, maybe one of each. All right, so that's linear runtime, constant space. All right, that's it. Hope you enjoyed the Boolean algebra. Feel free to like, subscribe, comment, and see you next time.